My name is Juan Marino, and I am a graduate research assistant for the WVU pollution prevention team. And today I'll be presenting on energy efficiency. Well, the focus is on optimizing performance across key areas to improve overall energy efficiency in various industrial systems. We'll be exploring various systems within industrial settings and discussing some strategies to enhance their energy efficiency, to reduce energy consumption, and ultimately reduce costs. So by the end of this session, hopefully you have a clearer understanding of energy efficiency in industrial systems and the significant impact that these systems can have on your operations. So here's what we'll be covering today in our session on industrial systems and energy efficiency. I'll first start with an introduction to these systems, where we will discuss their role and importance in energy consumption. And this will give us a foundation to understand why optimizing these systems is crucial. Next, we'll dive into the core of our session, where I'll give some background information and optimization strategies for each of the 8 key industrial systems. I'll cover some of the essentials and explore how we can make these systems more efficient in terms of energy. After that, I'll briefly summarize the key takeaways from today's discussion, focusing on the principles of energy efficiency that apply across all systems. And finally, I'll open the floor for some Q&A session. This will be your opportunity to ask any questions if you have any, share your thoughts, or dive deeper on any areas that interest you. So what are industrial systems? Industrial systems refer to the critical infrastructure and equipment used in manufacturing and other industrial processes. But today I'll be focusing on only 8 key industrial systems. These include lighting, HVAC, boilers, motors, fans, compressed air, building envelope, and steam. Each of these systems play a crucial role in energy consumption and efficiency. So in the following slides, I'll dive deep into each one of these areas, and I'll explore how to optimize these for better energy efficiency. To get us started, let's look at the role of industrial systems and energy consumption. So industrial systems are responsible for a significant portion of energy use in manufacturing and processing industries. Whether it's powering machinery, or lighting, climate control, all of these systems are the heart of your facility energy demand. So this energy use directly impacts your operational cost, often making up a large percentage of facility expenses. But this is not only about cost. How efficiently we manage this energy also plays a crucial role in sustainability efforts, reducing the carbon footprint and meeting regulatory requirements. So in the following sections, I'll explore how to optimize these systems. As I discussed the role of its industrial systems in energy consumption, this pie chart at the bottom of the slide provides a clear visual of energy and how it's being used across different sectors. So you will not notice that the industrial sector is the largest slice of the pie, accounting for 32.4% of total energy consumption. This highlights just how significant industrial systems are in the overall energy landscape. When we talk about optimizing these systems, we're addressing a major opportunity for energy savings. By improving efficiency in areas like machinery, lighting, climate control, we can make a considerable impact not only on operational costs, but also on sustainability efforts. So these set the stage for a deeper dive we'll be taking into each one of these systems. So this slide highlights the importance of energy efficiency in industrial systems. So energy efficiency leads to significant cost savings by reducing energy consumption and directly benefiting the bottom line. But it also supports sustainability by lowering our environmental impact. So by combining these two, cost savings and sustainability, we can achieve true energy efficiency. This balance is key for both economic and environmental reasons, making energy efficiency a key point for any industrial operation. So now let's move forward to the industrial systems. In this section, I'll deep dive into each one of them, lay some groundwork by providing some background information, some key points, and then introduce some optimization strategies. So I'll briefly explain here each system to be discussed today before I do a deep dive. So lighting, this system enhances visibility in industrial settings and plays a significant role in energy consumption, especially in large facilities. Lighting systems typically require a modest initial investment, but they offer a short payback period, making them a key area for energy efficiency improvements. Then HVAC, which stands for heating, ventilation, air conditioning, are essential for maintaining comfortable and safe working environments. They manage temperature, air quality, humidity, all of which are crucial for energy efficiency, and optimizing these systems can lead to substantial efforts in energy use reductions. Then boilers. Boilers are essential for generating steam or hot water, which is used for various processes. The efficiency of these systems directly impacts on our overall energy consumption, making them a critical component for energy savings. The motors are often referred as the workhorses of the industry. They drive a wide range of equipment and processes. Their efficiency is vital for maintaining operational effectiveness and reducing energy use. Fans are used in ventilation, cooling, and various industrial processes. Fans play a crucial role in managing airflow as well. Compressed air is a common utility in many industries. It's used for powering tools, equipment, and processes. Building envelope usually refers to the physical barrier between the conditioned, which heat or cool interior, and the unconditioned exterior of a facility. A well-maintained insulated building envelope is crucial for optimizing heating and cooling efficiency, thereby reducing energy consumption. And lastly, steam. Steam is often used in various industrial processes, from heating to power generation. Now let's deep dive into lighting. So in order to understand lighting, we first need to go through different types of lighting, usually commonly used in industrial settings. So first we have incandescent lamps, which is the first image on the top. These are the oldest and the least energy efficient types of lighting. They're being phased out in many places due to their high energy consumption. Next are tungsten halogen lamps, which is the second image on the top, which are slightly more efficient version of incandescent lamps, but still consume significant more amount of energy. Fluorescent lamps, compact, fluorescent, and CFLs are known for their energy efficiency and long lifespan, making them a popular choice in industrial settings. Compared to traditional incandescent lamps and halogen lamps, they consume less energy, although fluorescent lamps come in three main types. These are T12s, T8s, and T5s. These refer to their tube diameters, 1.5 inches, 1 inch, and 5/8 of an inch, respectively. And these tubes also are available in different lengths, typically 2 feet, 4 feet, and 8 feet, allowing for flexibility based on the specific application. Then we have high pressure sodium lamps and low pressure sodium lamps. These are often used in street lighting and large outdoor areas. They're efficient, but their color rendering isn't really that good, making them less ideal for some indoor applications. And metal halide lamps are another common type, known for the bright light output and efficiency, often used in large indoor spaces like houses. And finally, we have LEDs, the most energy efficient lighting technology available today. LEDs use a fraction of the energy compared to older lighting types and have much longer lifespan, making them preferred choices for new installations. In this slide, we're going to compare the wattage equivalent when switching from a traditional lighting type to LEDs, which result in energy usage reduction. So let's start with incandescent bulbs. A typical 60-watt incandescent bulb can be replaced with a 10-watt LED bulb, which provides the same light output, but with significantly lower energy consumption. For compact fluorescent bulbs, a 13-watt bulb can be swapped for an 8-watt LED, further reducing energy usage. Same thing with halogens. A 50-watt traditional bulb can be replaced with a 7-watt LED, leading to substantial energy savings. And lastly, fluorescents can be, for example, a 32-watt bulb can be replaced for a 15 LED watt bulb, and it can bring significantly amount of savings. And the chart at the bottom just visualizes these comparisons, truly showing that there is a reduction in energy consumption when you switch from traditional lighting to LEDs. And this change not only decreases energy, but it also contributes to sustainability by lowering overall electricity demand. So lighting accounts for around 20% of a facility's energy usage. Lighting has significantly low investment costs compared to other systems, which usually leads to shorter payback periods. And here's some of the most popular optimization strategies for lighting to find lighting savings. So first, like I said, upgrading to LED lighting from traditional lighting is one of the most impactful changes that can be made, since LEDs are much more efficient and they use up to 85% less energy and lasting much longer than traditional bulbs. Then secondly, implementing smart lighting controls is crucial. You can install occupancy sensors, daylight harvesting, automated dimming, and programmable timers, and other triggering switches to ensure that lighting is not only used when and where it's needed. So to ensure that lighting is used only where and when it is needed. This reduces waste and improves overall efficiency. And finally, optimizing the lighting layout, it's also a big one to match the specific needs of the space to ensure that there are not overlit areas, which can lead to unnecessary energy use. Now let's move on to HVAC systems. HVAC systems are essential for managing indoor climate control. In industrial systems, these systems control heating, cooling, and ventilation, and they're among the largest energy consumers in most facilities. As seen in this image, HVAC systems include motors, ducts, fans, controls, and heat exchange units. HVAC systems usually account for 20 to 35%, or even more in some cases, of the total energy consumed in many buildings. Also keep in mind that many of these facilities that have HVAC systems were designed and installed at times when energy efficiency wasn't really a priority. So most of these systems are designed to meet extreme load conditions, and they're oversized and maybe not operating efficiently. So let's break it down into both summer and winter, focusing on their key functions and the sources to achieve them. So in the summer, the primary goal of the HVAC system is cooling, right? The system works to remove heat from the air, which helps maintain a comfortable indoor temperature. An important part of this process is the humidification, where moisture is removed from the air to enhance comfort and prevent issues like mold growth. The sources used for cooling can vary, but typically include a chiller, a packaged unit, or a heat pump. Each of these systems is designed to efficiently extract heat from the air and expel it outside the building. On the other hand, during the winter, the focus on HVAC is for heating, right? HVAC systems just adds heat to the air, raising the indoor temperature to a comfortable level. During this process, humidification might be also needed, as heating the air can reduce indoor humidity, leading to dry conditions, and that can affect both comfort and health. Common sources of heat include gas-fired heater, boilers, and heat pumps. These systems are designed to generate and distribute heat throughout the building efficiently. And understanding these seasonal operations help optimizing the system's performance and ensuring a balanced indoor environment year-round. Now, these three are some of the most important key metrics that are used to evaluate an HVAC system efficiency and performance. So first, we have the COP, which stands for coefficient of performance. This one is the most important parameter to be measured and calculated. COP in HVAC measures the efficiency of heating and cooling systems, especially for heat pumps. So it's the ratio of useful heating or cooling provided to the electrical energy consumed. So higher COP indicates that the system is more efficient, meaning it provides more heating or cooling per unit of energy used. So for example, a COP of 2 means that for each 1 kilowatt of electric power consumed, 2 kilowatts of cooling effect can be delivered. It's important to mention that COP is not constant, but rather depends on the outdoor conditions. So as temperature changes, COP is also going to change. The second key metric is called the SEER, which stands for Seasonal Energy Efficiency Ratio, and this can be found on your HVAC unit, and it's usually on a yellow tag. This measures the cooling efficiency of air conditioning systems. It's calculated by dividing the cooling output in BTUs by the total electrical energy input in watts hours during the cooling season. So higher SEER ratings indicate more efficient cooling, which means lower energy consumption for the same level of cooling output. And then lastly, HSPF stands for Heating Seasonal Performance Factor. This measures the efficiency of heat pumps in heating mode over a heating season. So higher HSPF means that it has a better energy efficiency. So about 40% can be achieved in energy savings by implementing these strategies. So first, if you switch your current HVAC unit to a higher SEER unit, this will improve the cooling efficiency. Like I said in the last slide, a higher SEER rating means these units use less energy to achieve the same cooling effect, which can lead to substantial savings on energy bills. Secondly, implementing VFDs, which stands for variable frequency drives on motors, is another key strategy. VFDs adjust the motor speed based on real-time demand. VFDs will be discussed in the next slide a little further. Number 3, using smart controls such as programmable thermostats and building automation systems can dynamically adjust settings based on occupancy and external conditions. Number 4 is, of course, maintaining regularly. This is crucial for every industrial system, not only HVAC, for it to operate efficiently. Tasks like cleaning the filters, checking the ductwork, and ensuring proper insulation help maintain system performance and prevent energy waste. And then lastly, optimizing the airflow through proper system balancing and zoning ensures that each area of your facility receives appropriate heating or cooling without excess energy use. So let's make a quick stop here and let's discuss the variable frequency drives, because they will be mentioned further on the presentation. So VFDs are incredibly valuable devices in industrial systems since they allow us to control the speed and the torque of electric motors by varying the motor's input frequency and voltage. So there are 3 main key benefits when it comes to VFDs in energy savings. By adjusting this motor speed to match the actual load requirements, VFDs can significantly reduce energy consumption, often by 20 to 50%, depending on the application. In addition to saving energy, VFDs offer enhanced process control. These allow precise adjustments to motor speed. They help improve both efficiency and the quality of the final product. They also contribute to reduce mechanical stress of motors and equipment. Thanks to soft starts and stop functions, which minimize the wear and tear that typically occurs during startup and shutdown. You will find VFDs in various applications, including, like I said, HVAC, motors, pumps, fans, and conveyors, where they play a crucial role in optimizing performance and extending the lifespan of the equipment. Now let's move on to boilers. These are essential for generating steam or hot water in many industrial processes and heating applications. Boilers are typically among the top energy consumers in the facilities, especially in industries like manufacturing and food processing. We'll start with some key metrics to understand boiler and its efficiency. So first we have the AFU, which stands for Annual Fuel Utilization Efficiency. This is a standard measure of a boiler's efficiency in converting the energy, fuel into usable heat over the course of a year. So a higher AFU percentage means the boiler is more efficient and it's losing less energy as waste and converting more energy into heat. Another key metric is the combustion efficiency, and this measures how well the boiler burns the fuel. High combustion efficiency indicates that the boiler is effectively converting this fuel into energy with very minimal losses. And then steam quality, it refers to the proportion of steam in the output of the boiler. So high quality steam is essential for efficient heat transfer in many processes, and poor steam quality, on the other hand, can lead to inefficiencies and equipment issues. Some optimization strategies to improve the efficiency of boiler systems. First, upgrading to high efficiency units with higher APU ratings can significantly reduce fuel consumption. Modern boilers are designed to maximum fuel use, making them much more efficient than older models. Then, secondly, installing economizers is another effective strategy. Economizers, as you can see in this picture, they capture waste heat from the boiler's flue gases and use it to preheat the feed water entering the boiler. So in short, what economizers do is they reduce the amount of fuel needed to heat the water, improving overall energy efficiency. Condensing technology is a powerful efficiency booster. Condensing boilers recover latent heat from the exhaust gases, which will otherwise be lost and use it to preheat the incoming water. This can lead to substantial energy savings in facilities with high heating demands. Again, regular maintenance is key to keeping the boilers operating at peak efficiency. Routine tasks in this case can be inspections and cleaning of the heat exchanger surfaces, checking for leaks, making sure all the components are good and working. These steps also help prevent energy waste and to maintain the boiler's efficiency over time. And lastly, improving insulation around the boiler pipes, tanks, and other components to help minimize heat loss, ensuring that more of the energy produced by the heater is for its intended purpose rather than being lost to the environment. Let's move on to motors now. Motors are such a big part of industrial systems since they account for nearly 70% of the electricity used, making them the prime target for energy efficiency improvements. Let's talk about a little bit about what motors and some key facts. So motors are load-driven devices, which means that their energy use is directly tied to the demands of the equipment they power. So for example, if a motor driving a conveyor belt uses more energy when the belt is fully loaded than when it's running empty, that means it's a load-driven device. The motor rating refers to its maximum mechanical output, not its electrical input. This is important because the rating indicates how much work the motor can do, but not how much electricity it will use to do that work. So then the load factor is a crucial measure that compares the actual load on a motor to its maximum capacity. Motors operating at or near their optimal load factor are more efficient. Running on a motor significantly below its rated load can lead to inefficiencies and wasted energy. So now let's discuss some of the characteristics that makes motors more efficient. So first, utilizing more copper in the windings means less resistance, leading to lower electrical losses and less heat generation. This allows the motor to run more efficiently. Next, energy efficient motors have better fans and bearings. These components are more precisely designed and lubricating, reducing friction and helping the motor operate at cooler temperatures. The use of lower loss core materials is another key factor. So these materials minimize energy loss in the motor's magnetic core, further enhancing efficiency. And finally, the energy efficient motors are typically longer and heavier. We'll see that the extra size accommodates the improved internal components and allows for better thermal management, contributing to overall efficiency. So this picture is on the right. You can see a comparison of the three motors. A standard motor on the top of the image, an EPAC 1992 motor, and an energy efficient motor. So the EPAC 1992 motors were designed to meet the efficiency standards set by the Energy Policy Act of 1992. This legislation mandated minimum energy efficiency levels for electric motors, leading to better performance and reduced energy consumption across various industries. The act was a significant step forward in promoting energy efficiency, and it laid the groundwork for the more advanced energy efficient motors we see today. And then the motor on the right, it's an example of how energy efficient motor looks like with more copper and a heavier, bigger motor. When it comes to motor efficiency, the larger the motor, the higher the efficiency. This is because high efficiency in small motors is not really cost effective since they are load-driven devices. So one of the most effective strategies is to upgrade to high efficiency motors. These modern motors are designed to use less energy to produce the same amount of work as older models. So replacing inefficient motors with these newer ones can lead to significant energy savings. Also keep in mind that while the initial purchase cost of motors might seem significant, the majority of motors' total cost over its lifetime comes from operating costs. So typically accounting for up to 95% of motor total expenses due to energy consumption. If replacing the motors is not cost efficient, maybe start with improving and implementing and installing variable frequency drives. So again, what do? They allow you to adjust the motor speed to match the load requirements, which can dramatically reduce energy consumption, especially in applications where load varies over time. So for example, a pump running at a full speed only when needed and slowing down or stopping when diminished load can save a substantial amount of energy if the VFDs are being used. Also, making sure that your motors are the right size is critical. Motors are too large for the application often operate at lower load factors, leading to inefficiencies. So ensuring that the motors are correctly sized for their specific tasks helps avoid unnecessary energy use. And again, making emphasis on regular maintenance is essential in this case to keep the motors running efficiently. So this includes lubrication of the motors, utilizing the specific and amount and type of lubricant, checking for alignment issues, and replacing worn parts. Proper maintenance can prevent energy loss and extend the life of the motors. And lastly, it's not mentioned on the slide, but VFDs do come with self-starters, like I said in the previous VFD slides, and these are used to reduce the inrush current during the motor startup. So this not only lowers electrical stress on the motor, but it also reduces the overall energy consumption during the startup phase. And also stops also come with VFDs in some cases, which will reduce the overall energy consumption during the shutdown phase. Now, the next industrial system to be discussed are fans. Fans are a crucial component in industrial processes, particularly for ventilation and cooling. And among the various types of fans, like seeing this picture, you have mixed flow fans, HPLS, inline fans, and metal fans. The two most efficient ones out of these are the centrifugal fans and the axial fans. So let's focus on these two for a minute. Centrifugal fans are ideal for high pressure, low airflow applications, making them well suited for tasks that require moving air through complex ductwork or in environments where high resistance is present. And then axial fans, on the other hand, are designed to handle high airflow with lower pressure, making them perfect for large-scale ventilation needs where moving large volumes of air is essential. Now, the efficiency of fan systems depend heavily on their design, the setup of the system, and how these fans are used and operated. So factors like system resistance, which can come from the duct size or the bends, can increase energy use. Therefore, a good design and regular maintenance are crucial to minimizing the consumption. Beyond ventilation and cooling, there's another significant application of fan systems that specifically use centrifugal fans. This is for centrifugal industrial extraction. So the image on the right are actually fans that are being used for extraction purposes. So this process is vital in industrial manufacturing environments where it's necessary to remove hazardous substances such as oil, mist, fumes, dust, vapors, gases from the air to maintain a safe and clean workspace. So again, the efficiency of fan systems depend heavily on their design, like I said, and the setup of the system and how it is operated. So let's look at how we can improve these efficiency of fan systems. So again, installing VFDs. VFDs will allow you to adjust the fan speed to meet and match the demand, saving energy. Then optimize the airflow. Streamlining the airflow through ducts ensures that the system works efficiently without unnecessary energy use. So the effect of elbow throat on turbulence within a duct system and the sharp throat of image A here in the middle creates more turbulence than the rounded throat of image B. And then again, regular maintenance, making emphasis on these routine checks and maintenance keeps the systems running smoothly and prevent energy waste. Now let's move on to the next industrial system, which is compressed air. The US Department of Energy estimates that about 10% of the electricity generated for industrial manufacturing in the United States comes from air compressors. So this is interesting because most of compressed air systems are less than 20% efficient. So this makes me question, are compressed air really needed for some particular processes? Is there a substitute? In this image, you can see that compressed air systems, about 93% of the energy that inputs the system gets lost along the way. So leading to only 7% of the energy remaining. So look at the beginning of the diagram. Just in the air compressors at the beginning, air compressors 1 and 2, 80% of the energy that inputted the system is already lost. And then there are significantly losses happening along the way. That energy is being lost. So it's important to optimize the system. And how are we going to do that? So you have leaks that also account for a significantly amount of energy being wasted here. 25 to 30% of the air used in compressed air systems is lost in just air leaks. So fixing them is one of the most cost-effective improvements. Also a big one, if possible, eliminating the needs of these compressed air systems. Maybe opting and looking for more efficient compressors, upgrading to more energy efficient will definitely reduce the energy consumption. Maybe optimizing the system pressure, ensuring that the systems operate at the correct pressure will prevent excess energy use and equipment wear. And then lastly, implementing a recovering waste heat system. Since 85 to 90% of compressor input energy is lost as heat, implementing a waste heat recovery system will make a difference from an energy saving standpoint. The next system to be discussed here is building envelope. So building envelope is also referred to the shell or the skin of a building, but this accounts for external walls, roof, foundation, windows, doors, and any other openings. And it does play a crucial role in energy efficiency, particularly in terms of heat transfer. So heat conduction is the primary way heat moves through the building envelope, right? Several factors influence the amount of heat that is lost or gained through conduction. And these are the exposed surface area. So the larger the surface area that is exposed to different temperatures, the more heat will be conducted through the building envelope. So for example, if you have a large window, this will allow more heat to transfer than a smaller window. Then another aspect here is the temperature difference. So the rate of heat conduction increases as the temperature difference between the inside and the outside of the building becomes greater. So this is why well-insulated buildings perform better in extreme weather conditions, because they minimize the impact of temperature difference. And the third aspect here is material properties. So there are a lot of materials that are being used for constructing walls, roofs, and windows, and picking the best ones with better insulation and R values, which will be discussed here in a little bit, is critical. So different materials have different levels of conductivity, of thermal conductivity. So for instance, metal conductors heat much more efficiently than wood, leading to higher rate heat being lost or gained. So to assess how well this material receives heat transfer, we use the R value. The R value is a measure of material's insulation properties. It's important to note that the R value is the inverse of conductance. So the higher the R values means better insulation and less heat conduction. On the right side of this slide, you will see a diagram that illustrates best practices for optimizing the building envelope design. And I'm just going to name a few because I think it's really hard to see it. But one of them is 2 layers of foam with staggered seams to stop air and insulate. Another one is the roofs have to stand up to water and heat. Another one is blown-in insulation fits all sizes of voids and cavities, and ventilation allows hot air to escape. So now we're going to go over an example on how to calculate the R value of a wall. So in this example, we have a concrete wall that incorporates foam board insulation, which is a common method for improving thermal efficiency of a building envelope. So first, let's look at the image and let's understand the different layers that make up this wall from the inside to the outside. So this diagram shows that the wall includes several components. On the inside of the wall, there is an interior film, and this has a coefficient R value of 0.68. Next, we have a 4-inch poured concrete wall, which has an R value of 0.52. Since concrete isn't really a great insulator, this is why extra insulation, the foam board, is necessary. So after the concrete, 4 inches of concrete, we have 2 inches of foam board insulation. And this has a high R value of 10. This material significantly reduces heat transfer through the wall. On the exterior, there's a 0.5 inch of stucco, which is a construction material made of aggregates, a binder, and water. Then this has a small R value of 0.10. Finally, the wall is completed with an exterior film coefficient that has an R value of 0.17. Now, if we add up all these values, we get the total R value. In this case, is 11.47. This R value is measuring the material's ability to resist the heat flow. So the higher the R value, the better the insulation. This slide exemplifies how each layer contributes to the overall thermal resistance of the wall, with the foam board providing most of the insulation. Understanding these values by understanding these values, we can make informed decisions on what materials to use during construction of our buildings to improve energy efficiency. Now, infiltrations through building envelope increases HVAC costs and reduces comfort. So these leads to uncomfortable high and low temperatures inside a building. So let's talk about some optimization strategies for optimizing the building envelope. So to fix the building envelope, first we need to look and identify leaks. So there's a test which is called the blower door test to identify leaks, and this can be performed by using a fan to create pressure differences. This fan will reveal gaps that compromise energy efficiency. So first, you can improve insulation by fixing leaks, sealing gaps and cracks. Sealing any gaps and cracks in the building envelope will help prevent air leakage, improving energy efficiency. And adding or upgrading insulation in walls, roofs, and floors can significantly reduce the heat being lost. Also, upgrading windows and doors minimizes drafts and prevents heat from escaping. So the benefits of all of these, you're going to reduce energy consumption. A well-insulated and sealed building uses less energy for heating and cooling, reducing the overall energy consumption. You're also going to improve the indoor comfort level by maintaining a more consistent indoor temperature. You're going to create a more comfortable environment for your occupants. And you're also going to lower the HVAC load, which less heat loss or gain, HVAC system doesn't have to work as hard, leading to lower energy cost and extended equipment life. The next industrial system is steams. So steam is significantly used in industrial systems. It's essentially water vapor produced when water is heated to its boiling point, and it's one of the most effective ways to transfer energy in industrial settings. So this is why steam is a core component in a wide range of industrial processes, from power generation to food processing and chemical manufacturing. Steam systems are incredibly versatile, but to get the most out of them, they must be managed carefully. The efficiency of the steam system hinges on three key main areas. These are steam generation, steam distribution, and steam utilization. So steam generation, this is the process of converting water into steam, and this usually happens with boilers, inside the boilers. The efficiency which we generate steam directly affects energy consumption. So the goal is to produce steam using the least amount of fuel possible. Steam distribution is, so once the steam is generated, steam needs to be distributed to various parts of the facility. So efficient distribution minimizes heat losses, which can occur through uninsulated pipes or leaks in these pipes. And lastly, steam utilization. So like I said, steam is used in various processes. This include heating, drying, or driving mechanical systems. So making sure that steam is used at the right pressure and temperature is critical for our process efficiency. And there are also important metrics that we need to monitor to maintaining steam system efficiency. So the first one is steam pressure. This is the pressure at which steam is being delivered to the process, and it is vital to maintain the correct pressure because operating at higher than necessary pressures can waste a lot of energy. The second metric is steam quality. This metric refers to the moisture content in the steam. So the higher quality steam with less moisture is more efficient at transferring energy, leading to a better process performance. And lastly, the condensate recovery. After the steam has been used, it condenses back into water. So instead of discarding this condensate, it can be recovered and reused in the boiler, which will save energy and reduce water usage as well. So understanding how optimizing these aspects of steam systems can help reduce energy consumption and improve operational efficiency across the industrial processes. Now, there are important metrics that we need to, I was looking at the wrong thing. Okay, so steam also deals with a lot of leaks. and condensate systems are a major source of energy loss. So identifying these leaks in condensate systems leaks are critical. So here are some of the common sources where these leaks typically occur. So steam traps passing dry steam. When steam traps fail, they can allow live steam to escape instead of returning condensate to the boiler. So this will lead to significant energy losses. Also valves. Over time, these valves can develop leaks due to the wear and tear, allowing steam to escape through the valves. Then expansion joints. These components accommodate thermal expansion that can become leak points if they're not properly maintained. Then drip legs, condensate collection points that can leak if the piping is compromised. Flange connections and bends. There are areas where pipe sections join are particularly susceptible to leaks, especially at bends where the stress is higher. Tanks. Leaks can also occur at various points in tanks, especially where piping is entering or exiting the tank. And lastly, heat exchangers. Internal and external leaks in heat exchangers can lead to both energy loss and reduced system performance. So by regularly inspecting these systems and common sources, you can address leaks promptly. And you can therefore significantly improve the energy efficiency of the steam systems, thereby reducing the cost and enhancing the system reliability. So some optimization strategies, again, managing the leaks and the condensate, maintaining regular maintenance of the steam traps, insulating the pipes, reduces the heat loss, which in turn improves and reduces fuel consumption. And as well as improving the boiler efficiency. So like we discussed, upgrading to a high efficiency boiler or optimizing existing ones can make a significant impact on energy use. So let's wrap up this presentation by recapping what we have covered today briefly. So first, we took an in-depth look at the key industrial systems. We talked about lighting, HVAC boilers, motors, fans, compressed air, building, envelope, and steam. And we talked about the significant impact on energy consumption. We explored each system, understanding how they function and where the opportunities for energy savings lie in each one of these systems. And then we discussed some practical optimization strategies. The main goal of this session was to equip you all with the knowledge and strategies needed to make the most important industrial systems efficient. Also remember that energy efficiency and prevention and pollution prevention is all about optimizing industrial systems to reduce energy usage and pollution emissions and reduce the energy expenses.